Tonight, imagine standing beneath a sky so clear it feels like a window where every star is a message and every message is late. Light is the fastest thing in the universe, and yet on cosmic scales it's heartbreakingly slow. That single fact turns the night sky into a museum of the past, and it may explain why the universe can be full of life and still feel silent. In this documentary for sleep, we'll drift from the moon's 1-second delay to the minutes of the solar system, the years between stars, the deep time of the Milky Way and the horizons of an expanding cosmos, until distance stops being a number and becomes a feeling. If you enjoy calm science stories and cosmic mysteries, please like this video and subscribe for more. Now let's begin. A desert plateau rests under a sky so clear that the stars seem gently sharpened. Inside a small observatory, the lights are low, the air is cool, and a telescope turns with slow, careful motions. The dome opens like a quiet eyelid, and the night pours in without sound. In moments like this, the universe looks close. Bright points feel like ornaments on a nearby ceiling, and the mind supplies a comforting story. Light is fast, space is open, and distance is something that future machines will simply defeat. Yet the same starlight that feels intimate is also an old messenger. The night is a map made of delays. A few questions drift into view, calm and unhurried. How can the fastest thing in nature still feel slow? What does distance become when it is measured in time instead of in meters? And if every message must ride on light, what kind of connection is possible between stars? The first answer is simple and quietly satisfying. Even the nearest places already reveal the rule. Moonlight takes a little more than 1 second to cross the space between the moon and Earth. That pause is small, yet it is real. It turns any back and forth exchange into a rhythm of waiting. Sunlight takes about 8 minutes to arrive, meaning the warm glare on an afternoon field is already a memory that is slightly old. For a moment, everything is still. As attention moves outward, the delays lengthen in a smooth progression. Light from Mars reaches Earth in only a few minutes when the planets come near, and in much longer minutes when they pull apart. Jupiter's reflected light takes tens of minutes to arrive. Neptune's light takes hours. The solar system, often pictured as a neat diagram, becomes a wide clock face where each world sits at a different time. This is why the speed of light can feel both magnificent and modest at once. In empty space, light travels roughly 300,000 kilometers each second. That pace is beyond anything made of engines and metal, and it remains steady with an almost serene stubbornness. Yet the spaces between worlds are so large that even that speed must be given minutes and hours to do its work. A soft comparison helps the sounds settle without strain. A beam of light can circle Earth more than 7 times in a single second. That seems like pure speed, effortless and complete. But the same beam needs minutes to cross the inner planets and hours to reach the cold outskirts where small bodies drift. Speed is not only about motion, it's about what the landscape demands. Nothing urgent happens here. A spacecraft far from the sun can drift in long silence, its panels angled toward a faint warmth, its instruments humming quietly. Even if such a craft moves faster than any probe now travelling the gulf to the nearest star remains. The nearest star system lies a little more than 4 light-years away. Those words sound almost friendly, as if they describe a short stroll, but a light-year is a duration. It is the distance light covers in 1 year of uninterrupted travel. Here the second question takes shape. If light needs years to reach the nearest star, what does that imply for a message, for an exchange of knowledge, for a simple greeting? A signal does not merely cross space, it enters a corridor of time. By the time a reply returns, seasons of cycled children have grown, and the sending civilization has already changed in small and ordinary ways. The clarity is gentle rather than bleak. Communication at light speed is possible, and it is astonishing, but it is never immediate across interstellar distances. The universe permits connection, yet it insists on patience. In that insistence, there is a strange kind of calm. No conversation can rush, no misunderstanding can be corrected instantly, and no relationship across stars can be maintained by impulse alone. Another idea waits behind all of this, like a dim star behind thin cloud. The speed of light is not just a practical limit. In modern physics, it is tied to the structure of space and time, the pace at which influences propagate and cause follows effect in an orderly way. It is a constant that links distance and duration, as if the universe uses it as a quiet exchange rate between where and when. For a moment, everything is still. That thought brings a comforting realization. The limit is not a gate placed in the path to frustrate ambition. It is part of the same framework that lets stars burn steadily, atoms hold together, and chemistry build complexity. A universe with a radically different light speed would not be a faster version of this one. It would be a different cosmos with different balances, different rhythms, and perhaps no stable stage for life to appear at all. So the night sky becomes two things at once. It is a distant neighbourhood full of places that remain beyond ordinary lifetimes. And it is an archive bringing histories forward in the form of photons that have travelled for years and far longer. Looking up is not only looking out, it is also reading time. Outside the observatory, the wind is gentle. The dome's rim cools under starlight, and the telescope continues its slow tracking, following a point that drifts almost imperceptibly. The screens glow softly, and the universe offers its first lesson with quiet kindness. Even the fastest messenger takes time, and time is part of the message. A small lamp turns on in a quiet room, and the light seems to fill the space at once. The walls appear immediately, the corners become visible, and the mind registers the change as if it happens without travel. In daily life, light feels like presence, not like motion. Yet even here, the messenger still moves. It simply moves so quickly across such short distances that the delay hides beneath attention. A few meters become a breath too small to notice, and the brain rounds it down to nothing. For a moment, everything is still. Outside, the same illusion continues. A flash of lightning can be seen long before thunder arrives because sound creeps through air while light races through it. The contrast feels dramatic, and it teaches a calm lesson. Speed only becomes meaningful when distance is allowed to speak. So where does light's finitude begin to matter for a civilization on one small world? The answer is closer than it seems, woven into ordinary technology. Satellites, radio towers, and long cables all live inside the same rule that starlight obeys. Even when messages travel as electromagnetic waves, they still need time to cross space. Earth's circumference is about 40,000 kilometers. In empty spacelight, it can circle that distance several times in a single second. That sounds like perfect speed, yet modern communication does not always travel through vacuum. Much of it travels through glass fibers, and in glass the signal moves more slowly than in empty space, closer to about 2/3 of light's vacuum speed. Nothing urgent happens here. This quiet slowing shapes everyday experience in subtle ways. A message sent across an ocean requires measurable time, not because machines hesitate, but because distance insists on a small payment. Conversation still feels immediate because the delay remains shorter than human reactions, yet it is never truly zero. Even on Earth, every connection carries a tiny echo of space. A different scene makes the principle feel cleaner. In a dim control room, a spacecraft's status glows on a screen. A command is prepared, checked, and transmitted. The signal leaves as a radio wave, invisible and calm, expanding into the dark at light speed. Then there is waiting, because a reply cannot arrive until the outgoing message arrives first. Before the distances become grand, space already sets the rhythm. The Earth-Moon system is the first gentle threshold where that rhythm becomes obvious. Light takes a little more than 1 second to travel from Earth to the Moon. A round trip takes a little more than 2 seconds. A conversation across that gap is possible, but it cannot flow freely. The pause becomes part of the cadence, like the space between slow footsteps. For a moment, everything is still. On the Moon's surface, small reflectors left by earlier explorers still return laser pulses sent from Earth. A pulse departs, crosses the gap, touches the mirror, and returns. The measurement is not only distance, it is time turned into distance. The Moon's orbit becomes a clock hand traced in light, and the near universe becomes something that can be timed with patience. In a laboratory, that pause can be felt. A detector waits in silence after the pulse is sent, and then, after the small gap of time, the returning flash arrives like a quiet tap on the door. The universe answers, but always after a delay. From there, the mind can drift back to Earth and notice how often modern life depends on careful timing. Navigation systems rely on clocks that agree with extraordinary precision. Signals from satellites arrive at slightly different moments depending on where a receiver rests, and those differences reveal position. A ship on a dark sea, a plane above cloud, a phone in a quiet street all lean on the same constant that governs the stars. A soft curiosity follows as you are time itself stable for every observer. Relativity answers that time is not a single global river. Motion and gravity change its flow by small but real amounts, and practical systems quietly correct for it. The universe remains consistent, yet it is not rigid in the way intuition expects. Nothing urgent happens here. This is comforting in its own way. The cosmos does not hide special rules in the deep. The same physics that guides a satellite signal also guides a photon leaving a distant sun. The difference is not in the law, but in the scale. Seconds become minutes, minutes become hours, and the steady speed that once felt limitless becomes simply finite. Light also behaves differently in different materials. In air, water, and glass, it slows and bends. In vacuum, it moves at its universal pace. That contrast matters because the space between planets and spacecraft is mostly empty. When a signal leaves Earth for a probe, the emptiness becomes a clean corridor where light travels without friction, without fatigue, without detours. The mind can now lean outward beyond the familiar pauses of seconds. If a little more than 1 second reaches the moon, then a few minutes reach nearby planets and longer spans reach the outer worlds. The solar system begins to look like a landscape of growing delays where the same constant remains steady and the distances do all the changing. Outside the observatory, the night stays calm. The lamp inside stays warm and steady, and the telescope tracks a point that drifts almost imperceptibly. For a moment, everything is still. The next distances remain close by cosmic standards, but the clock face of space is about to widen from seconds into long, unhurried minutes. A long antenna stands in a wide desert, pale against the night. It does not rush. It turns with slow, careful patience, as if listening for something that arrives on its own schedule. Nearby, a low building hums softly as with electronics, and a few screens glow like small moons. In places like this, the solar system becomes a set of distances that can be heard as delays. A command leaves Earth as a radio wave, and then there is a pause that belongs to geometry, not to human choice. The signal must cross a widening gap, and the reply, if a reply is possible, must cross it again. A calm fact sits at the center. The time a signal needs is called light time, and it grows in a simple way. Double the distance and the delay doubles. Nothing mysterious is required. It is the same rule that makes the moon answer after a couple of seconds, only stretched into minutes and hours as targets drift outward in their orbits. For a moment, everything is still. Mars is often spoken of as a near neighbour, and compared with stars it is. Yet even this closeness carries a gentle distance penalty. When Mars and Earth come near, a radio message needs only a few minutes to arrive. When the planets separate to far sides of the Sun, the delay grows to many more minutes. A rover on Martian soil cannot be guided like a little vehicle in a nearby room. Each instruction arrives late and each confirmation returns late, so the machine learns to handle small choices by itself. That necessity produces a quiet consequence: the farther a civilization reaches, the more independence its machines must have. Close to home, constant supervision is possible. Farther out, supervision turns into planning. A probe becomes less like a remote-controlled object and more like a travelling laboratory, carrying routines, safeguards, and a steady sense of what to do when silence lasts longer than expected. Beyond Mars, the clock face widens. Signals to Jupiter take tens of minutes depending on where the giant planet sits along its path. The reply takes just as long, so a single question and answer can stretch toward an hour. Saturn lies farther still and the pauses lengthen. Uranus and Neptune rest at such distances that a message can take hours to arrive and the return can take hours more. In the outer darkness, communication becomes an exchange of postcards, not a stream of sentences. A small puzzle naturally appears. How does one steer a spacecraft accurately when every correction is learned late? The answer is patient prediction. Flight teams estimate where the craft will be when a command arrives, send instructions that assume that estimate, and then measure the craft's later response. The path is refined in small steps, not because the engineers hesitate, but because information arrives on a schedule set by light. For a moment, everything is still. The same schedule shapes science. When a spacecraft passes a distant world, it often gathers far more data than it can send immediately. Instruments keep working while the transmitter drips information back to Earth over weeks and months. A brief flyby can become a long season of downlink, as if a few minutes of experience must be unpacked slowly, one quiet packet at a time. This changes how Discovery feels. A moment that is immediate for the spacecraft arrives on Earth as a layered story first, a faint confirmation that everything is well, then cleaner measurements, then images and spectra that take their time. The mind learns to enjoy delayed knowledge. It learns that the universe does not provide instant updates but careful deliveries. Navigation for deep space uses this patience as a tool. Signals are sent and returned, and their travel times reveal distance with extraordinary precision. Time becomes a ruler. A spacecraft far from Earth can be located by comparing when a signal reaches different antennas on the rotating planet. Earth itself becomes part of the measuring instrument, turning quietly as it listens. A gentle question follows from all of this: if minutes and hours already separate the planets, what does travel look like for objects made of metal and fuel rather than light? The answer is steady and unhurried. Spacecraft do not cruise at anything like light speed. Journeys to nearby worlds are measured in months and years, and journeys to the outer planets can be measured in many years. The solar system is navigable, yet it is not quick. This slowness is not failure. It is a kind of motion that fits within limited energy and within the realities of carrying mass. Engineers borrow momentum from planets through gravity assists, shaping long arcs that look like patient calligraphy. A craft can leave Earth swing past one planet, then another, each time gaining speed relative to the Sun, without carrying an enormous supply of fuel. The technique feels almost like sealing, using gravity as a quiet wind. In the desert control room, the screens continue to glow. A faint signal arrives from far away, translated into data, then into meaning. Somewhere beyond the outer planets, a small machine continues its slow rotation, its antenna aimed toward a tiny bright point that happens to be home. Nothing urgent happens here. The pauses grow longer, the distances grow calmer, and the edge of the solar system begins to feel like a threshold into deeper dark. A faint spacecraft signal arrives with a thin, steady tone, as if it carries its own quiet patience. Far from the Sun, the craft spins slowly, keeping its antenna pointed toward a bright speck that is no longer a point of light, but a remembered direction. The background is dark, cold, and almost empty, and it does not press. It simply waits. In the outer solar system, speed begins to feel like a strange kind of success. A probe can cross the distance to the great planets in years, then continue outward past worlds that once seemed like final boundaries. Each milestone is real and each one is earned. Yet the same journey reveals a deeper truth. Even heroic speed remains small when the map is drawn in stellar distances. For a moment, everything is still. The difference between planetary travel and interstellar travel is not a difference of ambition. It is a difference of scale that changes the meaning of far. A planet is a neighbour within one star's domain. A star is an island separated from other islands by an ocean with no shores. The solar system can be crossed with careful planning, gravity assists, and patient propulsion. The space between stars asks for something else entirely. A calm comparison keeps the mind steady. Consider a probe leaving the neighbourhood of the outer planets at tens of kilometres each second. That pace is astonishing by everyday standards, and it continues for years without stopping. Yet at that pace, the distance to the nearest star is so large that the travel time stretches beyond any ordinary human schedule. Nothing urgent happens here. The nearest star system, aside from the Sun itself, lies a little more than 4 light years away. A light year is the distance light covers in 1 year of uninterrupted travel through empty space. So 4 light years means that even light needs a little more than 4 years to complete the trip. For anything slower than light, the years multiply. At this point, the imagination often reaches for a shortcut. It wants to believe that a better engine compresses the gap. Yet energy and mass do not negotiate easily. To move faster, a craft must carry more propellant or find a way to draw power from outside itself, and both demands grow harsh as speed rises. The solar system already teaches this lesson gently. Interstellar space repeats it with far more emphasis. For a moment, everything is still. Another comparison brings the number into focus without strain. The fastest human-made objects travel at a few tens of kilometers each second relative to the Sun. At such a pace, reaching the nearest star requires many tens of thousands of years. The result is not dramatic. It is quiet arithmetic applied to a distance that refuses to become familiar. Some future concepts imagine a craft reaching a small fraction of light speed, perhaps a tenth, perhaps a little more. In that gentler dream, the nearest star becomes a journey of decades rather than millennia. Even then, the details remain demanding. The craft must carry power long enough to accelerate and find a way to slow down again, instead of simply passing through. A higher speed, even sparse interstellar dust becomes something to account for with careful design, not fear, just engineering. Nothing urgent happens here. The nearest star has an almost intimate name. Proxima Centauri means the nearest of the Centaur stars. It is close in cosmic terms and still unimaginably far in human terms. The universe offers the nearest star and then shows what nearest means when the unit is a year of light. Between stars, space is not perfectly empty. A thin scatter of hydrogen, rare dust and faint fields fill the gap, but they do not form a road or a cloud. A spacecraft would coast through an emptiness so sparse that the scene barely changes. Star patterns shift slowly. The sun dims into an ordinary star. For a moment, everything is still. That stillness creates its own quiet difficulty. Human experience is built around journeys with horizons, a coastline, a ridge, a city at the end of a road. Interstellar space has no such markers at ordinary speeds. It offers no changing landscape, only time and a slow redefinition of what home means. In a gentle thought experiment, a craft leaves the outer planets and then coasts for years. Behind it, the solar system shrinks into a single direction. Ahead, the target star remains a point that grows only very slowly for a very long time. The traveller does not see a new world arriving. The traveller sees a long patience unfolding. Nothing urgent happens here. Communication offers no escape from this slowness. Even if a craft moves far faster than any probe today, its messages still travel at light speed. As distance grows, the lag becomes years. A report sent from halfway to the nearest star arrives years after it is written, and any reply arrives years after that. The mission becomes a chain of delayed moments stitched together by calm persistence. Far from the sun, the spacecraft keeps rotating in the dark and the antenna keeps pointing back toward a pale, familiar star. The signal drifts across the vastness, reaching Earth as a whisper that is already old by the time it is heard. The night remains calm. For a moment, everything is still and the map quietly expands from minutes and hours into years of light as the nearest star waits with a steady, patient glow. A long table sits in the middle of a quiet room, its surface cleared as if for a gentle experiment. A window is slightly open, and cold night air moves in with almost no sound. On the table, a few simple objects wait: a piece of fruit, a grain of sand, a small bead, a thin thread. Scale is difficult for the mind because it refuses to stay in one shape. The same distance can feel tiny when it is crossed in a day, and immeasurable when it is crossed in a lifetime. So the mind borrows tools from the hands. It shrinks things down, lays them out, and lets the body understand what the brain alone cannot hold. For a moment, everything is still. One can imagine the sun reduced to the size of an orange, warm and bright in the palm. In that shrunken system, Earth becomes a speck closer to a pinhead than to a marble. The pinhead does not sit beside the orange. It rests several meters away because even in a modest model, the space between a star and its planets is mostly emptiness. This first arrangement feels almost friendly. The orange sun on a tabletop, a tiny Earth at the end of a short walk, the other inner planets as smaller specks between them. The mind can hold it without strain. Nothing urgent happens here. Then the model continues outward. Jupiter becomes something like a small bead placed far across the room. Saturn sits farther still, a slightly smaller bead. The ice giants appear as almost negligible grains at distances that begin to ask for corridors and quiet hallways. Even so, the whole solar system still fits inside a handful of rooms. It is large, but it is not yet unthinkable. A soft curiosity arrives if the solar system can be walked across in minutes, in a scale model. Why do the stars still feel unreachable? The answer is not hidden in the planets at all. It waits in the space between oranges. For a moment, everything is still. Keeping the same scale, the nearest star does not sit at the far end of the house. It does not sit at the end of the street. It sits at the end of a long journey across a country. The second orange is placed not in the next room, but in a distant city separated by mountains, highways, and dark stretches of night. The gap between the two oranges is almost entirely nothing, and that nothing is the real shape of the local cosmos. This is the moment the model becomes emotionally clear. The planets are crowded close to their star. The stars are lonely. A solar system is a small campfire with a scattering of stones. The next campfire is far beyond the reach of ordinary footsteps. Nothing urgent happens here. The point is not to find the perfect scale. The point is to feel how the ratios behave. Most diagrams of space compress emptiness because empty space is difficult to draw on a page. Models show the opposite emptiness dominates. Matter becomes a set of tiny islands in a wide ocean. The mind also learns something subtle about speed. In the orange model light, crossing the Earth's sun distance can be imagined as a few relaxed breaths. A spacecraft crossing the same distance takes far longer, like a slow trip that lasts through seasons. But between oranges, even light takes years, and any slower craft takes far longer than human life expects. Speed does not fail. It simply meets a landscape built on different proportions. For a moment, everything is still. This mapping produces a gentle humility. It becomes clear that the familiar idea of a neighbouring star is a phrase shaped by language, not by scale. Neighbour means near enough for casual exchange, near enough for shared culture, near enough for quick help. The nearest star is none of those things. It is near only in the sense that everything else is even farther. Stars cluster in loose groups, yet the typical separation remains measured in years of light. A civilization might imagine spreading from star to star, and in principle it might. But the act resembles planting seeds across an ocean with a slow wind. It is not a stroll. It is a long patience multiplied many times. Nothing urgent happens here. The models also change the feeling of the night sky. Each point of light becomes less like a decoration and more like a distant campfire across a plain so wide that the plain itself cannot be seen. The darkness between the lights is no longer background. It becomes the main feature. It becomes the thing that shapes travel communication and the pace of discovery. In the quiet room, the orange notices nothing because an orange is not a sun. But the model does something important. It gives the mind permission to stop forcing the universe into familiar proportions. Once that permission is granted, the distances stop feeling like a trick. They become a calm fact, steady as the night. Outside, the real sky holds its scattered fires. Inside, the simple objects remain on the table. The thread lies in a gentle curve. The bead waits in silence, and the orange rests without urgency. For a moment, everything is still, and the next empty span beyond the nearest star begins to take on its full quiet scale. A drafting room stays awake while the rest of a building sleeps. A few desk lamps pool warm light over paper. On a wall, a star map is pinned with calm precision, and a single line is drawn from a small dot marked home toward another dot marked target. Between them is mostly blank. In that blank, the idea of travel changes. It is tempting to picture distance as something conquered by a stronger engine, as if speed is the only ingredient. But in deep space, travel is also about what happens at the end of a journey. A craft that can accelerate is only halfway to becoming a visitor. To arrive is to slow down again. For a moment, everything is still. The simplest way to feel this is to imagine a stone thrown across a quiet pond. The throw supplies energy and direction. But if the stone must stop at a precise spot without splashing past it, the throw must be matched by a gentle breaking. Space is not a pond, yet the principle remains: a mission is not only a launch, it is also an arrival. This is why engineers speak about delta V, the change in velocity a spacecraft can achieve. It is a calm accounting of possibilities. If a craft must speed up to leave home and then slow down to meet a new world, it must pay twice. The outbound acceleration is one payment, and the braking is another. Nothing urgent happens here. Fuel makes this accounting feel sharp. Carrying propellant is like carrying the abilities to change speed, but propellant itself has mass. More propellant means more weight to push. To bring fuel for braking, the craft must also accelerate that fuel during departure. The result is a quiet feedback loop. Extra fuel requires extra fuel, and the mass can swell until the design becomes a kind of heavy riddle. This is the heart of the rocket equation, though. It does not need to be written to be understood. The faster a craft hopes to go, the more dramatic the required mass ratios become. At modest speeds inside the solar system, clever staging and efficient engines can manage the trade. At speeds approaching a significant fraction of light's pace, the trade becomes severe. For a moment, everything is still. The next gentle hook appears almost like a practical question whispered across a table. If braking is so costly, why not simply avoid it? The answer is that many proposed interstellar probes do exactly that. A fast flyby can pass through a distant system and collect data during a brief window. It does not settle into orbit. It does not linger. It is more like a comet of technology flashing past and continuing onward. This offers a satisfying clarity. Speed is easier when arrival is not required. A flyby mission is an act of sampling, not an act of inhabiting. It can be scientifically valuable and it can be realistic, but it is not the same as visiting a place in the human sense of the word. Nothing urgent happens here. If lingering is desired, the problem shifts from how to go to how to stop. Several quiet ideas appear, each with its own patient logic. One is to carry propellant for braking, accepting the mass penalty. Another is to use the destination system itself as a brake, borrowing momentum from its star and planets through careful gravitational maneuvers. Yet another is to interact with the thin medium between stars. A magnetic sail could spread an invisible field and let the sparse interstellar plasma push back slowly over long distances. Each of these methods asks for patience rather than drama. Braking in interstellar space is rarely imagined as a sudden action. It is imagined as a long, gentle deceleration that begins far before arrival, as if the craft starts to prepare to meet the system long in advance. For a moment, everything is still. There is also the elegant idea of a sail driven by light. A powerful beam from the home system can push a reflective sail, accelerating a small probe without the probe carrying heavy fuel. This shifts the burden from the spacecraft to the civilization that launches it. The craft becomes light and swift while the home system supplies the energy. But the sail reveals the braking problem in a new form. A beam from behind can push. It cannot easily pull. Once the craft is far away, the beam must remain precisely aimed across enormous distances, and any attempt to slow down may require a second beam waiting at the destination, or a sail that can be turned to catch the destination star's light as a brake. A star is bright, but from far away its pressure is gentle. Braking becomes possible, but it becomes slow. Nothing urgent happens here. Another soft hook emerges from the physics of motion itself. Kinetic energy grows rapidly with speed. Doubling velocity does not simply double the energy needed. It multiplies the demand in a stronger way. And as speed creeps closer to light's limit, the energy required rises even more steeply. This is not a punishment. It is simply how the universe keeps its accounts. So mission design becomes an art of choosing what matters. Is the goal to pass by and glimpse a world, or to slow down and study it? Is the craft a tiny messenger carrying a camera and a transmitter, or a heavy laboratory with shielding power and long-lived instruments? The choices are not only technical, they're about patience, about what kind of knowledge is worth waiting for. For a moment, everything is still. In the drafting room, the line on the star map remains thin and quiet. A second line appears beside it, marking the long distance needed not for speeding up but for slowing down. The journey begins to look less like a single arrow and more like a gentle arc: accelerate, coast, decelerate, then drift near the destination long enough to observe. This yields a calm, satisfying takeaway. The universe does not merely demand speed, it demands symmetry. A craft that intends to arrive must plan for both halves of motion. The there is inseparable from the stop. Outside a real spacecraft imagined, or real moves through a darkness that offers no friction and no help. Stars shift almost imperceptibly. The destination remains a steady point ahead. Time seems to stretch, nothing urgent happens here. And somewhere in the quiet arithmetic of distance and light, the idea of arrival becomes what it truly is, in deep space, not a moment but a long patient easing into a new sky. A clock rests on a laboratory bench, its ticking almost too soft to notice. Nearby another clock waits in a padded case prepared for a small journey and a careful comparison. Nothing about either object seems cosmic. They simply mark moments one after another with quiet reliability. Yet the universe does not treat time as one rhythm shared everywhere. Time follows rules that are simple, exact, and sometimes surprising. When motion becomes extreme, the surprise is not dramatic. It is precise, measured in tiny differences that only instruments can reveal until those differences are carried into the distances between worlds. For a moment, everything is still. On a familiar street, time feels uniform. A person walks, a train glides, an aircraft crosses an ocean, and clocks appear to agree. The differences are too small to sense, but physics keeps careful accounts. When something moves, its clock ticks slightly more slowly than a clock that remains at rest. This effect is called time dilation, and it is tested again and again. A gentle proof floats above Earth. Navigation satellites carry clocks so accurate that tiny drifts would blur positions on the ground. Those clocks move quickly in orbit, which slows them a little. They also sit higher where gravity is weaker, which speeds them a little. Engineers correct for both influences, and the system works because the universe keeps its promises. Nothing urgent happens here. As speed rises, time dilation grows. The closer motion comes to light's limit, the more moving clocks slow relative to clocks left behind. A calm thought experiment gives this a clear shape. Imagine a spacecraft that can cruise between stars at a speed very close to light speed. Inside the ship, routines continue, instruments hum, meals are prepared. Sleep and waking cycle steadily. Through a small window, the starfield looks steady, almost unchanged, because the vast distances make even swift motion feel gentle and slow. From the crew's perspective, time feels normal. The ship's clock measures what physicists call proper time, the time experienced along the ship's own path. Far away, the home system's clocks advance more quickly. More years pass there than pass on board, even though both sets of clocks behave perfectly according to their local rules. For a moment, everything is still. This can sound like a secret way to make the universe smaller, but the trade is subtle. From home, the ship still needs many years to cross interstellar distance because it never reaches or exceeds light speed. What changes is the traveller's experience. For them, time compresses. A voyage that lasts decades for home can feel like only a few years on the ship if the speed is close enough to light's pace. Why does this happen? Space and said time are not separate stages. They form one space-time fabric, and motion changes how that fabric is divided into distance and duration for different observers. The speed of light acts like a conversion factor in this geometry. Keeping light's speed the same for everyone forces moving clocks to accumulate less time between the same events. Nothing urgent happens here. This geometry also explains the well-known twin scenario. One twin stays near home, while the other travels outward at high speed and later returns. The travelling twin ages less. The result seems paradoxical only when perfect symmetry is assumed. The traveller changes direction and follows a different path through space-time, and the universe assigns different amounts of time to different paths, like different road lengths between the same towns. In interstellar travel, this offers a strange possibility. A craft that moves extremely close to light speed could cross large portions of the Milky Way within one lifetime of ship time. Meanwhile, the home system might experience centuries. The travellers do not merely go far, they also step forward in history relative to home. The separation is not only measured in light years, but in eras. For a moment, everything is still. Time dilation is not only a story for imagined starships, nature demonstrates it softly. High in Earth's atmosphere, fast particles are created by cosmic rays. Many reach the ground, even though by their own internal timing they should decay sooner. They survive because from the ground's perspective, their internal processes run slow when they move at extreme speed. There is, however, no free escape hidden here. Time dilation does not permit faster than light messaging. No signal outruns light. And reaching speeds close to light's pace demands extraordinary energy and careful engineering. Even the thin dust between stars becomes something to account for not with fear, but with shielding, planning, and patient design. The universe can make the traveller's time feel shorter, but it does not remove the effort required to move that quickly. Nothing urgent happens here. Back in the laboratory, the two clocks are placed side by side again. After a journey, their readings differ by a small amount exactly as predicted. The difference is not metaphor. It is a measured gap that quietly proves time is not one universal stream. Outside, the night sky holds its scattered lights. Some of that light leaves its stars long ago, carrying old information at a steady pace. Some future traveller moving fast enough for time to soften would still receive those photons in due course, never earlier than light allows. In that calm, limit distance can be endured and time can be reshaped, while the deep rules remain patient and consistent like the steady ticking of a clock in a quiet room. A wide photograph hangs in a quiet hallway, a pale band of light arcing across a dark sky, dust lanes like soft brushstrokes and a dense glow thickening toward one end. It is the Milky Way seen from within, not as a neat spiral floating in space but as a luminous river overhead. The image looks almost close enough to touch, yet it is a view of a structure so large that even light needs a long time to cross it. The step from a solar system to a galaxy is not only a step in distance, it is a step in the meaning of time. Around one-star worlds can be thought of in minutes of light and years of travel. Inside a galaxy, distance belongs to eras and motion belongs to deep patience. For a moment, everything is still. The Milky Way is a disk of stars, gas and dust arranged in a broad, flattened shape. From edge to edge, it spans about 100,000 light-years, while its thickness is much smaller, like a thin, glowing platter. The sun sits inside this disk, not near the bright centre, but out in the quieter suburbs in a region where stars are more spaced and the interstellar night feels wide. A soft curiosity grows from that placement. If the sun lives in the suburbs, what is the centre like? The centre is crowded and bright, threaded with dense clouds and crowded with stars. Farther out, the sky between stars opens. The same galaxy holds many environments at once, like a city with busy streets and quiet neighbourhoods, all connected by one slow rotation. Nothing urgent happens here. The galaxy is not a frozen picture. It rotates. Each star follows a long orbit around the centre, guided by the combined gravity of everything in the disk and beyond it. The sun's circuit is not a quick loop. It takes on the order of a couple of 100 million years to go around once. While continents shift and species change, the solar system drifts along a curved path carrying its planets like small lanterns moving through a dark park. This raises a gentle question. Does the Milky Way spin like a solid wheel? It does not. Inner regions and outer regions move differently, and the spiral arms are not rigid spokes. They are slow patterns of higher density, more like waves in a crowd than fixed beams. The sun's relationship to these patterns changes over long spans, slipping through regions richer in gas and dust, then back into clearer space. For a moment, everything is still. From the ground, the Milky Way looks like a band because an observer sits inside the disk. Looking along the disk means looking through a thick crowd of stars, and their combined light forms the bright river. Looking out of the disk above or below its plane means looking through much less material, and the sky becomes darker and more open. A simple geometry becomes a nightly experience, brightness concentrated in one direction, quiet darkness in another. Dust shapes the view without drama. Fine grains between stars absorb and scatter visible light, carving dark lanes through bright fields. In longer wavelengths, especially radio, those same regions can become more transparent. So the galaxy appears in layers, one version in starlight, another in radio glow, another in the gentle outlines of gas. Nothing urgent happens here. Inside the disk, the typical separation between neighbouring stars is measured in light years. Even in the Sun's calm neighbourhood, the nearest stars sit several light years away. That distance is small on the scale of the Milky Way and huge on the scale of travel. It makes each star system feel like an island, and it makes the whole galaxy feel like an archipelago scattered across a wide sea of darkness. A quiet hook follows. If the islands are so far apart, how does the galaxy still feel? Like one structure, gravity does not require closeness. It reaches across emptiness, binding the disk into a rotating whole. Stars may be lonely, but they are not unbound. They share a common fall around the same centre, and that shared motion gives the galaxy its calm coherence. For a moment, everything is still. The size of the Milky Way can be felt through light time alone. A signal heading toward the galactic centre, roughly 26,000 light-years away, arrives in a future so distant that ordinary human history becomes a thin layer inside the waiting. A reply, if one exists, belongs to an even deeper future. Conversation across such distances becomes something like archaeology, a message sent from one era and received in another. This does not make the galaxy empty. It makes it slow. It suggests that connection across it is fundamentally different from the quick exchange that life on one planet grows accustomed to. A civilization can map the Milky Way, understand its shape, and still accept that most parts of it remain separated by long delays. In a quiet observatory, screens glow dimly and a telescope tracks a dense star field near the galactic plane. Each pinpoint is a sun with its own local neighbourhood. The Milky Way becomes a city of lights built on immense spacing. And within that spacing, a young technological species begins to leave a new kind of trace. Not footprints of matter, but a faint expanding sphere of radio whispers moving outward at the same steady pace as starlight. For a moment, everything is still. The bright band holds above the horizon, and the first faint human signals continue their slow journey into the wide, rotating night. A quiet radio dish rests under the stars, its pale curve turned toward a patch of sky that looks empty to the naked eye. The dish does not make pictures, it listens. In its receivers, the universe becomes a soft weave of signals, faint background, hiss, murmurs of gas, and the occasional crisp human note from a spacecraft. Radio waves travel at the same fundamental speed as light, yet they move through the galaxy with a different ease. They slip through dust that blocks visible starlight, and they stretch into long wavelengths that can be gathered by wide antennas. Por un momento todo está quieto. A technological civilization discovers radio almost by accident. Sparks and coils produce static. Engineers learn that a message can ride on an invisible wave instead of a wire. At first, the goal is simple: reach the next town, the next ship, the next city. A planet becomes wrapped in its own chatter, and distance across a world begins to feel smaller. But the waves do not stop at the horizon. They rise into the sky and continue outward, spreading into space like ripples on a pond that has no shore. Year by year, that expanding shell grows by one more light year in radius. After many decades, it becomes a bubble of electromagnetic history around the solar system, thin, widening, and already faint. The bubble is not a hard edge. It is more like a fading gradient, stronger close in, weaker farther out, and shaped by which frequencies are used and how antennas point. Old television carriers, early radar sweeps, and routine broadcasts all mix together, thinning as they expand. Far away, what remains is not a clear voice, but a delicate trace that must be searched for with care. Nothing urgent happens here. The bubble sounds dramatic, but physics keeps it humble. As a signal spreads its power, thins across larger and larger area. A broadcast that is loud at home becomes a whisper after only a few light years, and it becomes hard to distinguish from natural cosmic noise. The galaxy is full of static radiation from stars' storms and the gentle afterglow of the early universe. This leads to a quiet consequence. If a civilization wants to be heard far away, it cannot rely on accidental leakage. It must speak on purpose. A focused transmitter aimed like a flashlight rather than a lantern can push much more power into a narrow beam. Planetary radar already behaves like this, touching asteroids and returning echoes that reveal motion and shape. For a moment, everything is still. Listening has its own advantage. A careful observer can gather faint signals by collecting them over time and over area. Hours of steady observation can pull patterns out of randomness. Multiple dishes can work together as an array combining their data, so that a wide region of Earth behaves like one larger instrument. The human radio bubble is often described as roughly a century in radius because powerful radio use has a history on that timescale. That means the earliest strong emissions have reached only a few dozen to about 100 light-years away. Within that volume there are many stars, yet compared with the Milky Way it remains a tiny neighbourhood, like a faint porch light in a vast city. Nothing urgent happens here. The bubble is uneven. Early transmitters are weak. Later transmitters are stronger but increasingly directional. Over time, communication shifts toward cables, fibers, and tightly aimed links between satellites and ground stations. In one sense, the civilization becomes quieter to the wider galaxy, even as it becomes more connected at home. There are moments when a planet speaks outward deliberately. A message can be encoded into a narrow band repeated carefully and aimed at a chosen star. The details matter less than the gesture, a species deciding that the silence is worth addressing, even knowing that any reply must take years to return. For a moment, everything is still. From the receiving side, the search for such gestures becomes a practice of calm discrimination. Natural signals are often broad and messy. An engineered beacon might be narrow in frequency, unusually steady, or structured in a way that looks intentional. Observers scan discard what matches earthly interference and keep listening. Even when no signal is found, the process teaches the voices of the galaxy so that an unfamiliar note would stand out. A satisfying truth settles in this quiet work. The speed of light does not forbid communication across stars, but it changes the meaning of conversation. A message to a nearby star takes years to arrive. A review takes years more. Exchanges become slow like letters between islands. What survives that pace is enduring information. Mathematics maps warnings and patient records. Nothing urgent happens here. It also becomes clear why the sky can feel silent without being empty. The human radio bubble is young. Most of the Milky Way has not yet had time to receive it, and much of what escapes is too weak to notice unless a listener is very close and very attentive. Other civilizations, if they exist, might be similarly quiet, either because they do not spill energy into space or because their strongest signals travel in narrow beams that rarely cross another world by chance. Above the desert, the dish continues its slow turn. Stars drift with the Earth's rotation. The receivers gather a thin rain of radio photons. The bubble of human radio history keeps expanding one calm light year at a time, while the larger galaxy remains vast and patient, holding its distance the way it holds its light. A quiet campus corridor holds the last warmth of evening, and one office stays lit behind a half-closed door. Inside, a researcher watches a screen where pale lines drift across a dark background. The lines are not pictures of stars. They are traces of frequency, a waterfall of radio noise, and every so often a sharper streak that asks to be understood. In rooms like this, a simple question returns not as a challenge, but as soft curiosity. If the galaxy contains so many stars, why does it feel so quiet? For a moment, everything is still. The question is often called the Fermi paradox. The Milky Way holds hundreds of billions of stars, many older than the Sun, and many likely hosting planets. Over long spans, it seems plausible that life appears more than once, and that intelligence arises at least occasionally. If that is true, then the mind naturally wonders why no unmistakable sign has arrived. On a nearby desk, a notebook lies open to a familiar kind of list. It is not an equation to be solved in one sitting, but a gentle inventory of uncertainties: how often planets form, how often chemistry becomes biology, how often biology becomes minds, and how long a technological phase lasts. Each factor is a doorway into research rather than a fixed number. The list does not promise certainty. It promises a way to think without rushing. The calm answer is that unmistakable is a demanding word. A sign has to be strong enough, distinct enough, and timed well enough to meet a listener. The universe does not forbid such meetings, but it does not make them easy. Nothing urgent happens here. Distance is the first reason. Even inside one galaxy, the typical gap between star systems is measured in years of light. A message aimed at a nearby star needs years to arrive and years more for a reply. Across thousands of light years, the delay becomes longer than many human histories. Communication can still exist at that pace, but it begins to resemble a record left for a far future rather than a living conversation. Quietness is the second reason. As signals spread, they thin. A broadcast that fills a city becomes a whisper after only a few light years, then sinks into natural cosmic noise unless it is focused and powerful. A civilization that becomes efficient may also become harder to notice because it stops wasting energy outward. It speaks inward through cables and tight beams, and the wider galaxy hears less. Time seems to stretch. A third reason is overlap in eras. A technological civilization may last a long time, or it may change quickly into something with different habits. Even if life appears many times, the window during which it emits easily detectable signals might be brief compared with the age of the galaxy. Two civilizations can be close in space and still miss each other in time, like two lanterns carried through a forest on different nights. To make this gentle, one can imagine the galaxy as a coastline at night with scattered houses. Some keep porch lights on for hours. Some light a candle for a moment and then go dark. Some use shades that spill no light outside. A person walking the beach sees darkness most of the time, not because there are no houses, but because the lights are intermittent, shielded, and far apart. For a moment, everything is still. There is also the matter of where and how to listen. A deliberate beacon is often not a shout in every direction. It is a carefully aimed lighthouse, bright along one narrow path and nearly absent elsewhere. A narrow beam can miss a planet by the width of an orbit and still pass near on a cosmic map. A sender must know where a target will be when the beam arrives years later, and a receiver must happen to be listening at that moment on that frequency with the right sensitivity. Radio is not the only possible choice. A civilization could signal with brief flashes of laser light with carefully shaped infrared patterns, or with engineered changes to starlight that a distant telescope might notice. It could leave traces in the chemistry of an atmosphere or in the waste heat of enormous machines. Yet every method has its own quiet difficulty. Beams must intersect, patterns must be recognized, and natural processes must be separated from artificial ones without haste or exaggeration. Nothing urgent happens here. This is why silence can remain consistent with many realities. It can mean that life is rare. It can mean that technology tends to become quiet. It can mean that signals are narrow beams that seldom sweep across another world by chance. It can also mean that the right message exists, but it is still travelling through interstellar darkness and has not yet arrived. In the office, the screen continues its slow scroll and the researcher waits with patient attention. The Milky Way rotates without hurry. In that rotation, there are countless paths a signal might take, countless moments it might arrive, and countless ways it might be missed. Silence does not have to be interpreted as emptiness. It can be interpreted as scale a wide ocean heard from shore where ships may exist far beyond the dark horizon. Outside, the corridor lights hum softly. The building rests. For a moment, everything is still and the quiet question remains gentle, while the larger darkness beyond the galaxy continues to open slowly without sound. A thin beam of light moves through a dark laboratory guided by mirrors that look like small moons. The room is quiet enough that the faint whir of cooling fans becomes part of the atmosphere. On a table, a vacuum chamber waits with its glass ports turned toward the ceiling, as if it is ready to hold a piece of night inside it. Light behaves with a peculiar steadiness. It does not tire, does not slow in empty space, and it does not care how long the journey is. That steadiness is why the same number keeps returning in every discussion of distance and delay, about 300,000 kilometers each second in vacuum. For a moment, everything is still. At first, that number sounds like an ordinary speed, merely very large. Yet physics treats it as something deeper than speed. It is not only how fast light travels, it is also the fastest pace at which any influence can travel, the fastest pace at which information can move, and the pace that quietly stitches cause to effect. This is one reason the universe feels orderly rather than chaotic. If influences could arrive instantly, events far apart could interfere without warning, and the idea of a before and after would blur. A finite speed creates a calm structure effects must wait for causes to reach them. In that waiting time gains direction and distance gains meaning. Nothing urgent happens here. In the 19th century, the calm surprise arrives through electromagnetism. Electricity and magnetism are discovered to be two faces of one field, and the equations describing that field predict waves that travel through empty space at a particular speed. That predicted speed matches measured light speed. Light is not a special substance rushing through the void. It is an electromagnetic wave, and it inherits the pace built into the properties of space itself. This is a gentle hook because it turns a limit into a signature. The speed is not chosen at random, it is encoded in the vacuum in how fields respond and propagate. It is as if empty space has a characteristic tempo. For a moment, everything is still. Then relativity arrives and makes the tempo unbeatable. The speed of light is found to be the same for every observer, regardless of how the observer moves. This is not a preference. It is a rule that forces space and time to adjust in order to keep that speed unchanged. Lengths contract slightly along the direction of motion, and clocks tick differently so that all observers agree about the pace of light in vacuum. A satisfying consequence follows. The speed of light becomes less like a maximum gear and more like a conversion factor between space and time. It sets how meters relate to seconds in the geometry of the universe. It is the constant that allows space-time to behave as one unified structure rather than two separate stages. Time seems to stretch. In that geometry, the idea of a light cone appears without drama. From any event, light can spread outward in all directions, forming the boundary of what can be influenced next. Anything inside that boundary can be affected in time. Anything outside it cannot be reached yet, no matter how urgent the desire. The boundary is not a wall made of material, it is a boundary of possibility. This gives a calm explanation for why faster-than-light messages are not merely difficult. They would break the structure that keeps cause and effect in order. In relativity, sending information faster than light can lead to frames of reference, where an effect appears to arrive before its cause. The universe avoids that confusion by keeping the boundary firm. Nothing urgent happens here. This is also where the familiar statement about mass becomes meaningful. Objects with mass can approach light speed, but reaching it would require an ever-increasing supply of energy. As speed rises, each additional step demands more than the step before. The accounting becomes severe near the limit. It is not a moral judgment. It is simply how space-time measures motion. In the laboratory, this limit is not seen in rockets. It is seen in particle accelerators. Tiny particles are pushed to enormous energies and their speeds creep close to light's pace. Yet even with vast machines and careful engineering, the particles do not cross the boundary. Instead, they store the added energy in other ways. Their momentum grows, and their behavior reveals the geometry that keeps the speed fixed. For a moment, everything is still. There is also a quieter place where the constant matters measurement itself. Modern science chooses stable definitions that rulers and clocks can be trusted. The meter is defined in relation to the speed of light and the second tying distance to time with the universe's most reliable pace. Instead of relying on a physical bar stored in a volt, measurement relies on a constant that appears to be the same everywhere. This choice has a soft elegance. It treats the cosmos as the ultimate reference. It says that a human civilization, small and temporary, can still anchor its units to something that does not belong to any one place. Nothing urgent happens here. All of this circles back to the original feeling light is fast and light is slow. It is fast because it is the quickest messenger available. It is slow because the universe is immense, and because the speed is not allowed to increase without unmaking the relationships that give reality its coherence. So the limit is not merely an obstacle to travel, it is part of what allows the universe to have a stable history. It helps atoms and stars exist within consistent rules. It allows distant events to remain distant in time, as well as in space, so that the cosmos can be read like a layered archive rather than a single instantaneous blur. For a moment, everything is still. In a quiet observatory, the dome remains open, and the telescope continues its slow, faithful tracking. Photons arrive from far away, each one obeying the same constant tempo. The night sky becomes a gentle illustration of a deep rule, The universe connects everything through light, but it connects it on a schedule. And that schedule, steady and unhurried, is woven into the fabric of space and time itself. A quiet library keeps its shelves in shadow, and one desk lamp makes a small circle of light on paper. 2 dots on the page represent 2 stars. A straight line between them represents the ordinary route measured in years of light. A second line drawn like a gentle curve represents a different question: can distance be shortened without breaking the universe? The question appears whenever light feels too patient. If a message needs years to reach even the nearest stars, the mind looks for a way to step around the long corridor instead of running down it. Physics does not treat these ideas as promises. It treats them as lanterns that illuminate the edges of what is known. For a moment, everything is still. One lantern is the wormhole. General relativity allows space-time to curve and fold, and in some mathematical solutions, 2 distant regions are connected by a throat like 2 points on a sheet brought close by a bend. The picture is calm and elegant. It suggests that a voyage to a far system might avoid crossing every light year in between. A soft hook arrives immediately. If the equations allow a bridge, why not simply build one? The answer is that mathematics can describe many geometries, but nature must choose which ones can exist stably. The simplest wormhole models tend to collapse pinching, shut before anything passes through. Holding a throat open appears to require exotic conditions, especially negative energy density, a form of gravity not produced by ordinary matter. Nothing urgent happens here. Negative energy is not pure fantasy, but it is elusive. Quantum physics allows small fleeting regions where energy densities dip below a baseline in carefully prepared situations. The Casimir effect shows that the quantum vacuum can be altered between closely spaced surfaces in a measurable way, yet the amounts involved are tiny and delicate. The leap from subtle laboratory conditions to a stable traversable wormhole is vast, and it is not clear that the required ingredients can be scaled up at all. Wormholes still matter as boundary markers. They force careful thinking about stability, energy conditions, and the relationship between geometry and matter. Even if no civilization ever crosses such a bridge, the attempt to understand it teaches what space-time demands. For a moment, everything is still. Another lantern is the warp bubble idea, often linked to the Alcubierre concept. Instead of pushing a craft through space faster than light, the idea is to reshape space itself, contract space-time in front of a bubble, and expand it behind, letting the bubble drift along while the craft inside remains locally calm. At cosmic scales, space already expands and distant galaxies can recede faster than light without violating relativity because they are not racing through space. The space between them grows. The appeal is clear if the universe can stretch space. Perhaps space can be shaped deliberately, but the obstacle returns in a familiar form. The simplest warp bubble solutions again call for negative energy in large amounts, and they raise difficult questions about control. How does a bubble begin and end smoothly? How is it steered? How does it stop near a destination without trapping signals behind horizons? These questions touch deep rules, not just engineering details. Nothing urgent happens here. Sometimes the imagination points to cosmic expansion and wonders whether it can be ridden like a current, yet expansion becomes dominant only across truly intergalactic distances. Inside galaxies, gravity binds stars and gas into a coherent structure, and space does not stretch in a way that offers a useful push from one nearby star to another. Causality is the steady thread behind every shortcut proposal. The speed of light is not merely a speed limit, it is the pace at which causes can influence effects. If information outruns light, different observers can disagree about the order of events in ways that allow before and after to tangle. Physics becomes careful here because the ordinary coherence of history depends on that ordering. A third idea often enters the conversation and needs gentle correction: quantum entanglement. Entangled systems share correlations that remain even when separated by large distances. The behavior is real and repeatedly tested. Yet entanglement does not provide a usable faster-than-light telephone. The outcomes cannot be controlled to encode a chosen message, and the correlations are only confirmed when ordinary signals later bring results together for comparison. For a moment, everything is still. A small payoff settles in. The universe permits astonishing patterns, yet it guards the light-speed boundary for information. The most exotic schemes do not so much defeat that boundary as reveal how central it is to a stable reality. They show that the limit is woven into how space-time prevents paradox, not merely into how engines perform. There are also quieter ways to face distance that do not require bending space-time. A probe can carry tools code and instructions and build what it needs from local materials when it arrives. Some proposals even imagine sending blueprints of life genetic information or machine-mediated reproduction so that arrival becomes construction rather than transport. These ideas remain speculative, but they shift the problem from speed to patience. Nothing urgent happens here. Outside the library, the stars remain where they are, and their light continues to arrive on time. Somewhere a telescope dome opens under a cool wind, and detectors gather photons from faint galaxies. The distant universe does not hurry, and the ideas on the desk do not hurry either. For a moment, everything is still, and attention drifts from local islands of stars toward the wider ocean of galaxies, where light carries not shortcuts but deep time. A telescope dome sits open under a calm sky, and the instruments inside do something that feels almost like listening with eyes. They do not reach out and touch distant worlds. They wait. They let the universe arrive. Light does not only bring images, it brings time. Every photon carries a timestamp hidden in its journey, because it can only arrive after it has travelled. This makes astronomy an unusual science. It is always a study of how things were never of the distant present. For a moment, everything is still. Close by, the delays are gentle. Moonlight arrives a little more than a second after it leaves the lunar surface. Sunlight arrives after a handful of minutes. A planet's reflected glow arrives after longer minutes, then hours as the solar system spreads outward. These pauses are small enough to feel like a curiosity, yet they reveal the basic rule: looking outward is also looking backward. The rule becomes more vivid with the nearest stars. Starlight from a neighbour arrives after years of travel. A bright star that seems fixed and familiar is already a quiet memory by the time it reaches a human retina. In the calm logic of light, a night sky is not a live broadcast. It is a library of delayed pages. Nothing urgent happens here. Even the most powerful telescopes cannot escape this. A larger mirror gathers more photons and a longer exposure collects them patiently, but the photons still carry the same travel time. Better instruments do not show the present of a distant galaxy. They show a clearer, deeper picture of its past. In this way, distance turns into a natural time machine. When a telescope looks toward a nearby galaxy, such as Andromeda, it receives light that left that galaxy about 2.5 million years ago. The image is not a trick. It is a genuine record from a particular era preserved by empty space and delivered across a long interval. For a moment, everything is still. This also means the present of faraway places is always hidden. A star can change today and the news may only arrive years from now. A distant cloud can brighten or dim, and the observation will belong to an earlier chapter. The universe is not secretive on purpose, it is simply large, and the messenger is finite. There is a quiet symmetry in this. Any distant civilization that watches the solar system would also see an older Earth. From far enough away, oceans and continents would appear as they were long before radio antennas and satellites existed. The sky does not offer a shared present. It offers exchanged pasts traded slowly in photons. Nothing urgent happens here. Looking farther back, the universe changes its style. Very distant galaxies appear smaller and stranger, not because the telescope is weak, but because those galaxies are young in the image being received. Their stars are still assembling, their shapes are still settling. The farther the gaze reaches, the more the cosmos resembles its earlier chapters, when structure is less tidy and the light is brighter. Time seems to reascend and stretch. A deep observation can even show many epochs in one frame. In a long exposure aimed at a seemingly empty patch of darkness, a telescope gathers faint smudges that turn into hundreds or thousands of galaxies. Some appear closer and more mature. Others appear tiny and reddish, their light stretched by expansion arriving from times when the universe is much younger. One quiet image becomes a layered timeline. There is a gentle satisfaction in this. The universe writes its own history in light, and space preserves the pages. Astronomers compare different distances and see different ages, then rebuild the story of how galaxies grow, how stars are born and fade, and how the chemical ingredients of planets become more common over time. For a moment, everything is still. The deepest page in this archive is not starlight at all, but a background glow that fills all directions. It is the afterglow of the early universe, cooled and stretched by cosmic expansion until it becomes microwave radiation. This background does not arrive from one star or one galaxy. It arrives from everywhere like soft fossil light carrying a portrait of the cosmos when it's very young. Because light is finite, there is also a boundary to what can be seen. There are regions so far away that their current light will never arrive because space between them and the observer grows too quickly. Yet even that boundary has a calm generosity. Within the visible sphere, the universe reveals billions of years of its own past. The limit does not erase the story, it frames it. Nothing urgent happens here. By seeing many epochs at once, near as late far as earlier cosmology becomes possible, the past turns into data delivered on schedule. Expansion can be measured, ages can be inferred, and the slow growth of structure can be traced without ever leaving home. The finite speed that makes travel hard also makes the sky readable. In an observatory, the dome remains open. Screens remain dim. A long exposure continues collecting a thin drizzle of ancient light. The data will be processed slowly, and the image will appear layer by layer until a distant structure becomes clear. For a moment, everything is still. The universe does not speak quickly, but it speaks continuously, and its oldest messages arrive with a quiet steadiness that can be trusted. A quiet diagram glows on a screen in a dark room, showing a grid that stretches while small dots drift apart. Nothing moves fast in the picture. The change is smooth, like ink slowly spreading in water. The universe expands not into surrounding space, but through the growth of space itself. Distances between faraway galaxies increase over time, even when those galaxies are not pushing themselves away like ships under power. The fabric between them lengthens, and light must cross a longer path than it once would have. For a moment, everything is still. This can feel strange because everyday life offers no direct analogue. Rooms do not expand while chairs remain at rest within them. Yet on cosmic scales, the universe behaves like a stretching map. A galaxy cluster can remain bound by gravity, holding together like an island. Beyond those islands, the general trend is separation, a steady widening that becomes part of the universe's long breath. A soft curiosity appears: can something recede faster than light if nothing can travel faster than light? The answer is calm. The speed limit applies to objects moving through space and to information moving between nearby points. It does not limit how quickly the space between very distant points can grow. Expansion is a change in the geometry of space-time itself. Nothing urgent happens here. This leads to a quiet boundary called a horizon. There are regions from which light can reach an observer, and regions from which light cannot, not because light refuses to move, but because the distance it must cross grows too quickly. The universe becomes a landscape with a visible domain and an unseen beyond, shaped by time, expansion, and the steady pace of light. The horizon is not only about what is seen tonight, it is also about what can ever be seen. There are regions whose light has not yet had time to arrive since the beginning, and there are regions whose future light will never arrive at all, because acceleration keeps pulling the path open faster than photons can cross. The observable universe is a kind of calm bubble of information. Beyond it, the cosmos can still exist in full reality, yet it remains permanently out of reach for observation. A gentle hook follows from the stretching road. While ancient light travels, space continues to expand, so the sources of that light can end up much farther away than they were when the photons began. The night sky becomes a meeting with distant objects as they used to be carried forward by a messenger that never hurries. For a moment, everything is still. Expansion does not only happen, it accelerates. Observations show that on large scales, the rate of separation increases over time as if a faint pressure within empty space encourages the widening. This component is often called dark energy, not as a final explanation, but as a name for the effect the cosmos speeds up its expansion. Acceleration changes what can ever be reached. Light emitted from some distant galaxies now may never arrive because the gap grows too quickly. Older light can still be seen, a fading postcard from when those galaxies are closer, but new messages fail to cross the widening distance. Nothing urgent happens here. The loss is quiet. A galaxy does not vanish in an instant. Its light is stretched to longer wavelengths and thinned by distance until instruments can no longer gather enough of it to form an image. The universe does not close a door with a bang. It closes it with a long, silent exhale. Even within this evolving geometry, gravity makes small refuges. Nearby galaxies in the local group remain close enough to pull on one another strongly. Over deep time, they can drift together and merge into a single larger system. From within such a merged home, the surrounding sky can grow emptier, not because the universe runs out of galaxies, but because the horizon hides them. For a moment, everything is still. In that far future, a civilization could look up and see mainly its own galaxy and a few local companions. It might not see the rich tapestry of external galaxies that fills modern images. Without that evidence, the wider story of expansion and cosmic beginnings could become harder to reconstruct. The universe would appear smaller and more self-contained, even if it remains vast. This makes the present era quietly special. It is a time when stars and planets are common, and also a time when distant galaxies are still visible in great numbers. The sky carries a deep archive, the growth of galaxies, the afterglow of the early universe, and the gentle signature of expansion itself. Nothing urgent happens here. A soft payoff rests in the perspective. The speed of light combined with expansion limits what can be reached and what can be known. Yet those same limits make the night sky readable. Light arrives from far away carrying earlier chapters, and the pattern of what is visible hints at what lies beyond reach. In the quiet observatory, the dome remains open and the air remains cool. Screens show faint arcs and slow curves, evidence of a universe that changes without hurry. A telescope gathers photons that began their journey long before any human instrument existed. The cosmos continues to expand, and still it offers its light as a patient messenger. For a moment, everything is still. The distant galaxies keep drifting, the local stars keep circling, and the horizon remains a gentle boundary. In a universe where light has a finite pace, seeing is always a meeting between now and long ago. A small planet turns beneath a thin atmosphere, and the night side is scattered with gentle lights. From far away, those lights would be almost nothing, one faint grain in a wide, dark sea. Up close, the scene feels intimate, weather, moving oceans, breathing and living, chemistry cycling in steady rhythms. The universe around this world does not rush. It allows motion and messages, but it also insists on a pace that cannot be bargained with. Light sets that pace not as a punishment, but as a rule woven into space-time. After long reflections on distance and delay, a softer question takes shape. What does this limit mean for life that wants to explore? For a moment, everything is still. One answer is practical and quietly hopeful. The speed of light makes the nearby home matter. A civilization may dream of other stars, yet the richest opportunities are often close moons with shadowed ice. Neighbouring planets with ancient riverbeds and asteroid belt full of raw materials. Icy worlds with hidden oceans and the long outer regions where comets drift. In a universe where interstellar travel is slow, a single star system is not a cage. It is a vast region with many frontiers large enough for centuries of exploration, engineering, and quiet discovery. One quiet twist is that staying near does not mean staying small. Within one system, resources can support habitats, observatories, and long-lived archives. Sunlight, rock, and distant ice can be turned into shelter and fuel. Slow expansion within a system can still feel like a widening world measured in decades rather than in light years. A gentle curiosity follows. Could a civilization become deep and wise without ever leaving its neighborhood? The sky suggests that it can. Stellar physics is learned from one star's spectrum. Planetary science is learned from local worlds and their atmospheres. Even cosmology comes by patience because light from far away arrives without requiring travel. A species can map galaxies, measure expansion, and reconstruct deep time by collecting photons in silence. Nothing urgent happens here. Another answer is social, and it arrives with calm logic. If travel between stars were fast and easy, the first civilization to master it could spread quickly, shaping others before they have time to grow. The slowness of light acts like a natural buffer. It gives each island of life a long interval to develop culture ethics and resilience without immediate interference. The galaxy becomes many separated experiments running in parallel, not by design, but by geometry. This buffering also softens everyday risk. Distant events do not arrive instantly. Consequences travel at light speed, and that means there is always delay, always a measurable window between cause and effect. Most of what matters for ordinary existence remains local and stable: seasons, tides, sunlight, and the slow turning of a planet. The universe may contain powerful phenomena, yet the nearest environment is usually quiet enough to build homes, libraries, and patient science. For a moment, everything is still. A third answer is philosophical, and it does not need to be heavy. The limit on speed creates an unusual kind of connection. The wider cosmos is known through traces, light gravity and faint particles that arrive after long journeys. Knowledge becomes an art of inference. Spectra become chemistry shifts, become motion, dim shapes become galaxies, and patterns become history. A civilization raised under such rules learns to value patience and careful revision. Certainty becomes something earned slowly, not seized quickly. Here the earlier themes gather gently. The silence of the sky can be compatible with abundance because signals thin and time windows are narrow. The horizon of expansion can hide distant regions, yet it also makes the visible universe feel precious. The steep energy cost of extreme speed can make reckless travel unlikely, yet it encourages elegant engineering, long planning, and durable systems that value longevity over immediacy. Nothing urgent happens here. There is also a quiet optimism in light itself. Light is slow compared with cosmic distances, but it is faithful. It travels straight in empty space, bending only where gravity guides it. It carries information with high integrity across immense spans. It delivers spectral fingerprints that reveal temperature, composition, and motion. In a sense, the universe sends postcards without being asked, and a small world can read them with modest instruments and persistent attention. A soft question appears at the edge of this thought. If direct contact with other minds is rare, does meaning shrink? Another possibility remains: meaning can expand even in solitude, because solitude does not prevent comprehension. A civilization can become a place where the universe is understood, where atoms organize into curiosity, where the long story of stars is reconstructed from ancient light. And if contact does happen, it may resemble a slow exchange of archives messages that arrive like time capsules carrying maps, mathematics, and patient introductions. For a moment, everything is still. In a night observatory, the sounds are small: the low whir of a mount, the faint hiss of radio receivers, the subtle click of a cooling system. These modest noises against an immense background resemble a handmade echo of cosmic ambience. They mark the presence of attention, and attention is one of the rarest products the universe seems to create. Outside, stars keep their steady positions. The galaxy continues its slow rotation. Distant galaxies drift outwards with the expansion of space. None of this feels urgent. It feels continuous. On a small world, night settles over rooftops, deserts, oceans, and observatories that keep watching. For a moment, everything is still, and the universe continues to send its light patient, ancient and quietly enough. Night settles into a steady hush, as if the universe lowers its voice. A small world continues to turn beneath a thin, protective sky, and the lights of distant stars remain where they are, patient points in a wide darkness. Somewhere an observatory stays awake with dim screens and slow motors. A telescope tracks without hurry. A radio dish listens without expectation. The atmosphere is simple, soft air, quiet machinery, and the gentle cosmic ambience of a vast space that never needs to speak loudly to be immense. For a moment, everything is still. Across the long journey of these reflections, distance becomes time, and time becomes a kind of landscape. The moon is a pause of seconds. The planets become minutes and hours. The nearest stars become years. The galaxy becomes deep time and the wider cosmos becomes a horizon, where light arrives as history. Nothing about this is rushed and nothing demands immediate answers. In that calm pace, the universe feels less like a problem to solve and more like a steady rhythm to inhabit. The speed of light remains firm, not as a threat, but as a quiet rule that keeps cause and effect in order that turns the sky into an archive that lets ancient photons arrive intact after long travel. A small civilization may remain local and still grow vast in understanding. It may never cross every distance and still learn to read the cosmos through the faithful delivery of light. It may never meet every possible neighbour and still find meaning in patient observation, careful thought, and the gentle wonder that comes from simply being part of the same universe that is being studied. For a moment, everything is still. The night continues, stars continue, space continues. On a quiet planet, rest becomes natural while the cosmos keeps drifting and glowing beyond every window and roofline, unchanged by urgency, steady enough to let sleep arrive.